As the world enters a new space age, engineers are actively working on advancing new technologies to propel spacecraft flight into the unforeseen depths of space. New developments in material sciences and chemistry unlock things that were never possible in the past and give life to new future technology that looks like it could be from Star Wars. Although there is a lot that the future has in store, let's look at technology that NASA has already been using to send probes to other planets and even into interstellar space. Although it's up to the primary stage of a rocket to get it off the ground and through the thick Earth atmosphere, it's up to the upper stages of a rocket to really move it into orbit, or past orbit toward another celestial body. Centaur upper stage is a liquid hydrogen burning upper stage that is usually mounted atop an Atlas V rocket, and historically on the Titan series rockets until their retirement in 2005. It is the first liquid hydrogen burning upper stage, being the first to successfully manage the volatile fuel in the vacuum of space, where its burn will take place. To explain some of the chemistry, the reaction of liquid hydrogen with liquid oxygen is a simple combustion reaction. Combustion reactions explode like they do because in reacting they release energy. According to thermodynamics, there are two kinds of chemical reactions: endothermic reactions and exothermic reactions. Endothermic reactions have final products that are at higher energy levels than the reactants, so they take in energy from their surroundings, making things cold. Exothermic processes have products with lower energy than their reactants, so they release energy, making heat. When you burn chemicals, it's an exothermic reaction. This is the reaction that makes rocket thrust possible. In addition to hydrogen being used as rocket fuel, you can use things like methane, or traditional rocket fuel, RP1, which is refined kerosene very similar to jet fuel. They also provide combustion reactions and require an oxidizer, but in the total reaction also produce carbon dioxide in addition to water vapor because of their carbon content. Back to the Centaur. Although the engine has been in development since the early days of rocketry in the 60s, its use has continued into the modern day, recently being used to take the Perseverance rover to Mars to begin its mission. The upper stage has both 1 and 2 engine configurations, but most commonly used in the 1 engine configuration. The engine has a specific impulse of 451 seconds, that being 7 minutes and 31 seconds, with the RL-10 engine producing 22,300 pounds of thrust force for the duration. These numbers coming off the RL-10 model coming specifically from the Atlas V. This extra long burn time, longer than most other upper stages, allows for payloads to be shot into space at crazy speeds, allowing for the exploration of the solar system with the use of automated probes. The Voyager probes, both launched on Titan III rockets using a Centaur upper stage, are both now in interstellar space. Despite its age, it still continues to be an incredible piece of technology and has greatly helped humanity explore the solar system. Ion drives sound like a super futuristic concept, but they've actually been around for decades now. In 1964, NASA would test the first ion thruster in space, named the Space Electric Rocket Test, or CERT in short. Although it only ran for 30 minutes, it proved that it was possible. CERT 2 followed in 1970 and greatly expanded this runtime, as well as its consistency. Jump forward 28 years, and the Deep Space One probe launched in 1998, and it marked the first resounding success of an ion drive in a spacecraft, successfully completing its mission into the asteroid belt. Ion drives work by ionizing particles. Ionization of a molecule or atom is when you change the charge of that atom by bombarding it with energy or with a collision with another particle. It either temporarily loses or gains an electron, meaning that a neutral atom with a neutral charge will now be either positively or negatively charged after ionization. In ion engines, specifically the one in Deep Space One, NASA used xenon atoms and bombarded them with electrons, causing the particles to become positively charged. Once the particles have a charge, powerful magnetic grids can accelerate them out the back at insane speeds, using them as propellant, causing a small amount of thrust, usually only a fraction of a newton. Although it's a small amount of accelerations, these engines, depending on how they're designed, can continuously accelerate for years at a time, meaning that tiny amount of force will do large amounts of work over time. To clarify, it isn't possible at the current time to get things into space using only this technology for the foreseeable future. Probes using ion technology must be put into orbit by a rocket, like Atlas V I used as an example earlier. The thrusters are there to continue increasing velocity once it's in space, also to maneuver the spacecraft if it needs to course correct. It sounds underwhelming, but thrusters like this have been seeing more and more use lately and are getting much stronger, most recently being used on the SpaceX Starlink satellite network, each satellite having a small ion drive that will allow for small adjustments in their orbits to provide a more consistent coverage of Earth's surface. And most impressively, the Dawn spacecraft launched in 2007 had an ion drive and was able to be the first spacecraft to orbit 2 different destinations, those destinations being Vesta and Ceres, 2 large asteroids in the asteroid belt. meaning that the ion drive was successful in maneuvering a probe into the orbit of one celestial body and successfully push itself out of that orbit into another, all using ion technology. To clarify, this was a single piece of hardware without any ultra-complex contraptions and staging. The Saturn V, which technically did achieve 2 orbits, specifically low Earth orbit, and then the lunar module, which orbited the moon, while the lander landed on the moon. But this was a 3-stage, 360-foot tall rocket, with several more separation events before returning to Earth. The fact that the Dawn spacecraft was able to maneuver into 2 different orbits and stay there for extended periods of time was truly an accomplishment. There are some cool upgrades coming to these technologies soon in the near future. I mentioned the Centaur upper stage. Well, ULA is actually working on a new rocket called the Vulcan Centaur. Not only will it use Blue Origin's new BE-4 engines, but it will feature an upgraded 2-engine Centaur upper stage, which according to ULA will release up to 2.5 times more energy than the past models. Also on the topic of endurance upper stages, the SpaceX Starship system, currently under development, will allow for in-flight refueling, so theoretically, it gets to cheat out of most fuel limitations and burn for as long as it can be refueled, which will be important considering that they're planning on sending this rocket to Mars. There have been some upcoming developments in ion propulsion technology. The next thruster will offer a significant boost in power compared to the NSTAR thruster, which was the one used on Deep Space One mission and the Dawn mission. It has a larger accelerator grid, and with the development of stronger batteries and more efficient solar panels, can use 3 times the power to accelerate the ionized xenon atoms, meaning far greater acceleration for the spacecraft. The next ion thruster is also more efficient and will have a longer mission lifetime than its predecessor. Now all this stuff relates to the near future, but what about further than that? I've neglected one thing so far, something that has eluded scientists for decades. The holy grail of propulsion technology, nuclear. So before I get into some possible ideas about using nuclear energy in space to propel us into further unforeseen locations, I'm going to have to go a little off topic and talk about the nuclear bomb. On August 6, 1945, the US dropped the first nuclear bomb on Hiroshima. The bomb leveled everything in a 2-mile radius of the blast. The bomb contained 64 kilograms of enriched uranium, but due to the inefficiency of the warhead, less than a kilogram of the substance underwent fission, meaning that less than a kilogram of uranium-235 generated the full energy of the blast, which released an estimated 63 terajoules of energy. As for how it works, atoms are held together by the 3 fundamental forces: the electromagnetic weak force, between protons and electrons, also between protons and the nucleus, offering outward force to counter the strong nuclear force between the neutrons and protons of the nucleus, holding the nucleus together, and gravity, which is present as the attraction of anything with mass. In smaller atoms, the strong nuclear force is the strongest, since the nucleus is compact and the electromagnetic force between protons is minimal. As atoms get bigger and have larger quantities of protons and neutrons in their nucleus, that electromagnetic repulsion between protons in the nucleus, sometimes called the weak force, becomes much stronger, as well as the strong nuclear force becoming weaker in a large nucleus, causing atoms to become unstable, which is why generally the heaviest atoms at the bottom of the periodic table are radioactive. Radioactivity comes with radioactive decay, which is the process in which particles like protons and neutrons are expelled from the nucleus, changing the weight, composition, and eventually completely changing the atom into another element. Fission specifically works when those radioactive atoms collide and break apart, releasing insane amounts of energy. Since they don't do this naturally, and naturally they slowly decay, these elements need to be brought to a state where this reaction occurs. This is called critical mass, or the point when fissile material begins the chain reaction of exploding. Critical mass is usually achieved by implosion, which is an explosion with the intent of compressing the radioactive material to spark the fission reaction. From here, atoms break apart and release energy. The released particles then crash into other uranium-235 atoms, causing more fission, which is the chain reaction. In nuclear reactors, this reaction is not intended to be an instantaneous combustion, but more a slow one intended to produce heat and run a generator using steam or another fluid. This reaction is slowed using control rods that absorb neutrons as fission occurs, keeping the mass of uranium-235 from exploding outright, but keeping its reaction going slowly. When these rods fail and the reaction loses control, that's when you get something like Chernobyl. How does this matter to rockets? Well, the idea is that if you can harness this power, you can have the most energy-dense fuel possible, which is something that rockets struggle with, as the balancing act between thrust, rocket weight, fuel weight is a difficult one, especially when trying to get large payloads up into space and beyond. Many have tried, but ultimately nothing of the type has been to space. There's some great ideas out there. One of them was actually Nerva here. I got it here. So this was a nuclear-powered engine. Mainly, it was functioned kind of like an ion engine, where there was no reaction between two chemicals. It was literally just a propellant tank with hydrogen passed through these exposed reactor cores, which were super hot. It was a fission reaction core. So basically that would give the hydrogen all the energy it needed and be shot out the back. And these things were super efficient. And they would run for like 20 minutes. Like I'm surprised that technology at the time wasn't utilized. They were being developed around the Apollo era, I believe, and they never ended up going to space. I think that's incredible. I think they really could have. So this was a really good design. This was actually designed by NASA. So I figured, why don't I end the video by trying to come up with my own. I'm not a rocket scientist yet. Alright, so this is MS Paint. The idea of combining a reactor to power an accelerator grid and an ion drive is not an original idea. That was actually planned at one point, I believe, but it ended up getting canceled. Reactors in space, not a new thing, but from researching all this stuff about fission and like fission products, I learned that xenon, specifically I think xenon 135, is a common fission product of uranium-235. So, and it's commonly a neutron absorber in reactions, like in fission reactors. So generally they want to vent it out and get rid of it in reactors. But if you're using it in space, we already know that regular ion thrusters are powered by xenon. So why not use your fission products as propellant for your ion generator? So also uranium is extremely dense. So, 1 mole of uranium, even if it's only what, like 6% xenon as a fission product, you're still getting, I feel like, enough volume to work with there. Also, it's super hot gas, and you can use the properties of a bell nozzle in a vacuum, which is pretty much the idea that the bell nozzle helps gases expand in a particular way, that it reduces the pressure but increases the speed. Which, I mean, like look at like a Falcon 9. Like the Merlin engines on the first stage have little bell nozzles at sea level, because obviously there's outside pressure, and if they had large bell nozzles it would be inefficient. But in space, where there's a vacuum, like where this would be running, because it's radioactive and dangerous to use on Earth, like the Falcon 9 or Falcon Heavy second stage has a very wide bell nozzle, because in space, as gas expands like that, it accelerates in that particular instance, like with the bell nozzles. So it's more efficient. And then you would use that same generator, the nuclear reactor, to power your accelerator grid for your ion drive, which would be using the fission products. So I don't know, I thought it was a good idea, maybe. Yeah, so that's my project. I kind of wanted to end it unscripted, so I hope you enjoyed. I learned a lot doing this. Hope you learned something new too.